In this video, we will talk about the Riemann integral. We will start by talking about partition of a portion of the real number line, and then we'll look at the upper sum of f with respect to a partition and the lower sum with respect to partition. We'll talk about upper integrals and lower integral, and then we'll talk about the Riemann integral. And then finally, we'll look at three different theorems. First is the theorem about refinements of partitions and how they affect the lower and upper integrals. Second is a theorem that says a lower integral is always less than the upper integral. And finally, because sometimes the definition is a difficult way to prove that something has a Riemann integral, we have a theorem that gives us a condition to tell us if something has a Riemann integral. The first thing we will do is talk about partitions of a closed interval of a real number line. And a partition of an interval is a set of points x0 through xn. So it's a finite set of points, so only up to xn, such that a is equal to x0, which is less than x1, which is less than x2, all the way up to is less than xn, and xn is equal to b. This definition of a partition is totally consistent with the definition of partition that we learned about way back in chapter 2 when we talked about partitions of a set, but this is a particular type of partition. In particular, it's a partition of a portion of a real number line. Here I have an example of a partition of the interval between a and b. So my partition is equal to the points x0, x1, x2, x3, and x4. So I have x0 has to equal to a, and x4, since this partition only goes up to n equals 4, so x4 is equal to b. And as you can see, the size, the length of each partition does not need to be equal. They can be different sizes. So again, here P is a partition of A, B. Here I have another partition, P1, x0, x1, and x4. So you can see that's what I have in blue. The first partition goes from x0 to x1, and then the last partition goes from x1 to x4. You can see that P and P1 partition the same interval, and P1 is a subset of P. So we call P a refinement of P1. And the idea of calling it a refinement is that when we're studying the interval between a and b, or the behavior of the function between the interval a and b, we can study the behavior in finer detail with this larger set, and hence p is a refinement of its subset. If the function f is bounded, then we can look at these partitions, and for each partition, for I equal 1 to n, we can let mi, capital Mi of f, it's dependent on the function, equal the sup of f evaluated at x for x inside the partition. So for each mi, we're looking at the least upper bound of the function. We can similarly define lowercase mi of f as the infimum, or the greatest lower bound of the function. And when only one function is under consideration, we could abbreviate these two without the f, so mi, capital Mi, and lowercase mi. Looking at an example for this definition, we are going to calculate mi for each I from 1 to n. So let's look at I equals 1. So we're going to calculate m1. And now we only have one function drawn here, so I dropped the f notation. And so m1 is going to be equal to sup of f of x for x in the interval I minus 1, which is x0, to x1. So between x0 and xi, we're looking for the least upper bound. And the least upper bound is somewhere here. Let's just assume this is the maximum. So right here, this would be our m1. Continuing, for I equals 2, then m2 is going to be equal to sup of f of x, where x is between x sub 2 minus 1, which is x1, up to x2. So between x1 and x2, I want to look for the least upper bound, or the max, essentially, of f of x. and that actually is this point right here. So this is M2. For the next interval, I'm looking for the greatest, the least upper bound, which is right here. This is M3. And for the last final interval, I have M4. Similarly, I can look for the lowercase mi, which is equal to the infimum of f of x in the interval. For I equals 1, we're looking for the infimum where it's the lowest, which is right here at m1. And then for m2, for this interval, m2 is right here. For this interval, the lowest point is right here at m3, and this last interval, the lowest point is over here. Now we are ready to define the upper sum of f with respect to a partition and also the lower sum with respect to a partition. So first we're going to let delta x sub I equal the length of the partition, that is x sub I minus x sub I minus 1. So the upper sum of f with respect to the partition, which we are going to denote u, f, p, because remember, this upper sum is with respect to a partition. There are many different ways to partition this, and you can see if we partition this differently, we would get different m1s and m2s. So UFP, this is with respect to a partition, is equal to the sum of each of the mi times the length of the interval. We have the corresponding definition of the lower sum with respect to p, which is equal to the sum of mi, lowercase mi, times the length of the interval. Essentially, what we are doing is getting the area under the rectangles for each partition. So here, for the upper sum, we have, for the first partition, we have the height at m1 times the length of the interval. So we have the area here of this rectangle. And then for the next interval, we have the height at m2 times the length of this interval, etc. So we have this blue curve here. I've also expanded out this notation here for this particular example. And just to contrast that, I did the areas of the rectangle for the lower sum of f with respect to p. And just to emphasize that this upper sum is dependent on the partition, I did a different partition here of my same function. A naught and x naught has to equal to a, and my last element of my partition has to equal to b. But I put x1 a little bit closer to x0 and x2 kind of in between. And again, I have a different number of elements in my partition here. You can see in this first interval, my rectangle looks sort of similar. It's a little bit narrower. But here in the second interval, I definitely have a much higher m2. This would be my m2. And this is my m3, this height over here. Over here is my m3. Here I have m2, so I definitely have a much higher m2 and a different look for my rectangle. And then here's my highest point in my last interval. And so you can see that these areas are not the same. Again, the upper sum and the lower sum always have this p because it is dependent on the partition. Now we were ready to talk about the definition of the upper integral and the lower integral. So let f be a bounded function defined on the closed interval ab. Then uf, and you notice there's no p, uf is equal to the infimum of ufp, where p is a partition of ab. So in other words here, ufp, this is the set of all upper sums, all possible upper sums, and the reason why there are many is because it is over all the possible partitions of AB. So UF is the infimum of the set of all these upper sums. And UF was the infimum of the upper sums, is called the upper integral. Similarly, we have a lower integral, and LF is the sup of all the lower sums across all the different partitions. In the case that the upper and lower integrals are equal, we say that f is Riemann integrable on the closed interval, and we denote their common value by, and you're used to this notation, the integral ab f of x dx. That is, if L of f equals u of f, then L of f equals u of f is equal to this Riemann integral. And again, I have this note here that UF is equal to the infimum of UFP, where P is a partition of AB. So UF is the infimum of all the upper integrals, and there are many upper integrals because there are many possible partitions. We had looked at this upper sum and this drawing for this graph in a previous slide, and I just want to reiterate that for the integrals, the Riemann integral, the physical interpretation of the integral corresponds to our intuitive notion of area under the graph of f between a and b, because our refinements can get refined enough that essentially these rectangles follow the curve f of x, and then essentially we have the area under the curve. So we've covered the basic ideas of the Riemann integral, and so now we have these three theorems to discuss. The first theorem deals with refinements and how they affect your lower and upper integrals and sums. So if f is a bounded function on the closed interval ab, and p and q are both partitions of ab, and q is a refinement of p, then the lower sum of f with respect to the partition P is less than or equal to the lower sum of f with respect to the refinement Q, which is less than or equal to the upper sum of f and the refinement Q, which is less than or equal to the upper sum of f and P. Rather than brute force memorizing this, I think this picture will go a long way in helping you remember what at least this part is, and then the analogous kind of drawing will help you remember the last part of this. Also, the proof is really helpful in really seeing what's going on. But let me just take a moment to talk about this picture. So I have my drawing of f of x here. Without the refinement, I have my my area in blue. The area in blue talks about the partition from xk minus 1 up to xk. So when I look for the minimum, the infima of the function value here, I have the absolute minimum for this entire interval over here at mk. So this will be the area that I'm calculating. Now, if I deal with the refinement q, so let's just put in another point here, so that makes q our refinement, you can see now for this small interval here, I have a different minimum, which is greater than my absolute minimum on the whole entire interval. Right now I have my entire interval from A to B divided into two sections. So this second section opens up the possibility for a smaller infimum of the f of x, and that actually is m star of k. And in this way, I actually get more area here, which is why the lower sum of the refinement will be possibly larger, so greater than or equal to the lower sum of p. But we should talk about all this in a formal proof. First, it follows that this middle part here, that the lower sum of fq is less than or equal to the upper sum of fq, this part follows directly from the definitions of the lower sum and the upper sum. To prove then this part of the inequalities, which was what we were looking at in the picture, we'll look at the lower sum of fp and compare that to the lower sum of fq. So suppose P is a partition, and consider P star formed by adding an extra point to our partition. So we add an x star somewhere in between x of k minus 1 and x of k. Here I have my first picture. So somewhere in this partition P, I have an interval xk minus 1 up to xk. And in that interval, I have my infima of f of x, and that would be mk. So this is my part of my original partition. So it's an interval in my original partition. But now we are going to form a new partition, P star, and we're going to add x star to that, and it's going to divide up this original interval into two intervals. Okay, and now x star and this P star, this so P star now is a refinement of P. We're looking, and it's called a refinement because we're looking at this interval in finer detail now. So again, kind of formalizing what I just said, if T1 is the infimum of f of x on our interval now on this half of x of k minus 1 up to x star, then I look at T2 is going to be my infimum of this half of my new interval that goes from x star to x of k, then T1 is either greater than or equal to mk, and T2 is greater than or equal to mk. In this case, in my drawing, T1 is equal to mk and T2 is greater than mk. But this is always going to be the case because my mk was the absolute infimum for the entire interval. So now my lower sum of p star and my lower sum with respect to p, they're the same except possibly over this interval here because I added this extra point. So LF of p star minus LF of p is equal to T1 times the interval length. So I have my T1 times the interval length, and my T2, my new infimum, times my interval length here, minus mk. And again, this part here is my LFP star, and this part here is my LFP. I did some algebraic manipulations here, and I also note that this expression has to be greater than or equal to 0 since all my terms are greater than 0. And therefore, what I have is that this LP star minus LFP is greater than or equal to 0, which then implies that LFP star is greater than or equal to LFP, which was what I was trying to prove. If our refinement Q contains R more points than P, we simply apply the same argument R times. So each time we add one more X. So after R times of applying this, here we did this adding X star. So we just add another point until we get to R, added all of our R points, and we'll get LFQ is greater than or equal to LFP. The argument for this side of the equation, that the upper sum of FQ is less than the upper sum of FP, is similar. Although now the refinement is going to be less than, since here in the non-refined partition, we're looking at the absolute maximum, whereas here in the refinement, we might get some supremum in the smaller intervals that are less than our absolute maximum, which is why now it is less than for the refinement. The refinement is less than the original P. We will do an example for this theorem here. Let f be a bounded function on the closed interval AB, and P and Q are partitions of AB. Prove that the lower sum of FP is less than or equal to the upper sum of FQ. And hint, we want to consider the partition P union Q, and notice that P union Q is a refinement of both P and Q, and is called the common refinement because it's common to both. Once we consider this refinement, then this proof here is a straightforward application of this theorem. And I noted that P union Q is the common refinement of P and Q. Now LF, the lower sum of F with P, is less than or equal to the lower sum of the refinement P union Q, which is less than the upper sum of F of P union Q, which is less than or equal to UF of Q, the refinement. So now we just take this part of our inequality with this part of our inequality, and we have shown exactly what we wanted to prove. One other comment in this example here, the results, the Q does not need to be a refinement of P. Just you want to know that the lower sum of one partition is always less than or equal to the upper sum of any partition, any other partition. Our next theorem concerns the lower integral is always less than the upper integral. Let f be a bounded function on AB, then the lower integral of f is less than or equal to the upper integral of f. We will look at the proof. We will start with the results from our last example and say the lower sum of one partition is always less than or equal to the upper sum of any other partition. In this way, you can consider the upper sum of FQ as being an upper bound for S, where S is the set of all the lower bounds for all the possible partitions of A, B. Thus, U, F of Q, is greater than the sup of LF, which implies that LF is less than UFQ for all partitions Q. And then we want to remember that LF is the infimum of UFQ, where Q is all the partitions, and so this is equal to UF. And that gives us that LF is less than UF. For our next example, we are going to use upper and lower sums to evaluate this integral of x squared dx from 0 to 1. And we are going to use the partitions 0, 1 over n, 2 over n, all the way up to n minus 1 over n, and 1. I have here the definition of my upper sum, as well as the definition of what mi equals. Then, the definition of the lower sum and little m of I is totally analogous. I have my graph of f of x equals x squared here, and just for an example, I took n equals to 4. And again, Pn here, we didn't specify that we're talking about n equals 4, but I just wanted to see what was going on. So you can see that my partition for n equals 4 is going to be 0, 1/4, 1/2, 3/4, and 1. And you can also see this partition divides up our interval into equal lengths. Each interval is of equal length, and the length is equal to 1 over n. And the other thing for the maximum, it's going to be the rightmost interval, rightmost value. So that's going to be the 1/4 squared. It's going to be the 1/2 squared, the 3/4 squared, and the 1 squared. And now I'm ready to look at my general upper sum of FP, which is equal to the sum from 1 to n. Again, the length of my interval is 1 over n times my maximum value, and the maximum value is going to be I over n squared, again, like I had shown in this example here. So this here becomes 1, I can pull out the 1 over n cubed, and then I have my sum from 1 to n of I squared. My lower sum is very similar, but I do need to look at my little mi's, and those are going to be because they're the minimum, they're always going to be the leftmost point. So it's I minus 1 over n, and that's the difference here. This theorem here is a convenient way of determining if a function is integrable. We, of course, have the definition over here that says it's integrable if the lower and upper integrals are equal. But this is an additional condition that we can have if this is hard to determine, and that is if f is a bounded function on the closed interval ab, then f is integrable if and only if for every epsilon greater than 0, there exists a partition of ab such that the upper sum of f with respect to that partition minus the lower sum of f with respect to the partition is less than epsilon. For my next example, I'm going to consider the function g of x is equal to 1 if x is rational and 0 if x is irrational. I am going to show g of x is not integrable by showing that the upper sum is not equal to the lower sum using this partition here of the interval 0 to 2. Because the rational numbers and irrational numbers are dense on the real number line, each subinterval is going to contain rational and irrational numbers. So mi is going to equal 1 for each interval, and the little mi is going to equal to 0 for each interval. This says that the upper integral of g with respect to p is equal to the sum of mi. Every capital Mi is equal to 1 times the length of the interval. And when we sum up all these intervals, we are going to get 2. So it's just 1 times length of all the intervals, which gives us 2. The lower sum is going to be equal to the lowercase mi, which is equal to 0 times the length of the interval, which of course is still 0. Now, since the upper integral does not equal to the lower integral, g is not integrable on 0, 2, on the interval 0, 2, by the definition here of what it is to be integrable. That is, the lower and upper integrals are equal, and in this case they are not. Remember that I had just said that this is the theorem we use to prove things are integrable? Well, here I was proving something was not. So I was using the definition and showing that this function does not meet the criteria. So the definition is great for proving things are not integrable. My last example before we have the review questions for you to try. Let f be continuous on the closed interval ab, and suppose that f of x is greater than or equal to 0 on the interval. Let the lower integral of f equal 0. Then we want to prove that f of x is equal to 0. I am going to do this by contradiction, so I'm going to assume there's a point C, I should have put C here, there's a point C where f of C does not equal to 0, and I'm just going to, for this part of the proof, I'm going to assume that f of C is greater than 0. And since f is continuous, which I have the definition of a continuous function here, that means for every epsilon greater than 0, there exists a delta greater than 0, such that f of x minus f of c is less than epsilon whenever x minus c is less than delta. And what I have done is I've chosen epsilon to be equal to f of c divided by 2. And then I just wrote in the rest of my definition. There exists a delta such that f of x minus f of c is less than f of c over 2, plugging in my epsilon, when x minus c is less than delta. And then I also kind of reinterpreted this by just taking out the absolute value sign. So x minus c is greater than minus delta, and it's less than delta. So I have x is between c minus delta and c plus delta. And now, just looking at this, I don't want the absolute value. So I am going to set f of x minus f of c less than f of c over 2 and greater than minus f of c over 2, which gives me f of x, adding f of c to both sides, is greater than 1/2 f of c and less than 3/2 f of c. And I'm just going to focus on this point here, which means that f of x is greater than f of c over 2. And now I am going to consider the partition A, c minus delta, c plus delta, and b. And I'm going to look at the lower sum. And again, the c minus delta, c plus delta, that is exactly the portion where f of x is greater than f of c over 2. So if I look at my lower sum, that's equal to my infimums times the length of my intervals. So for my first interval, I'm going to have 0 to a, and then I'm going to find my max, or my delta x and everything. I'm sorry, my min, my m1. And then for my next interval, that's going to be my c plus d to c minus d. So it's exactly this interval here. So I'm going to be looking for my m2, which is the infimum of f of x, where x comes from c minus delta, c plus delta, times the length of my interval, which is c plus delta minus c plus delta. Here I've noted, because I am in this interval, that this portion, my infimum of this, has to be greater than f of c over 2. And so the significance of this, you have your other terms over here, is that this whole sum has to be greater than or equal to 0, because here we have something greater than 0. But we also know that this lower sum has to be lower than our lower integral, which by the example, we were given that LF equals 0. So here we have a contradiction, so it must be the case that there's no f of c greater than 0. To review what we have discussed today about Riemann integrals, we started with the idea of a partition and then also a refinement of a partition. We talked about these like the sup of our function f, as well as the inf of our function f, and we denoted them with a capital Mi and a lowercase mi. We talked about the upper sum of f with respect to our partition, as well as a lower sum with respect to our partition. And then we defined our upper integral to be the infimum of our upper sums, where we consider all the partitions of AB. We defined our lower integral to be the supremum of are lower sums when we consider all the partitions of AB. And when the lower integral and the upper integral are equal, then we call that a Riemann integral, and we denote that with our normal integration sign, and that if LF, our lower integral, is equal to UF, then we say that this is our Riemann integral, and the F is integrable on AB. And then last, we had these three theorems. One, when we have refinements, how it affects our lower and upper sums. We also said that the lower integral of a function is always less than the upper integral of a function. And then last, we had a condition for integral. We can test if a function is integrable using this theorem here. Now I have 3 problems for you to try, so you can pause the video, give the problems a try, and then on the next slide I'll have solutions for you. These are solutions for the first 2 problems, and I also circled this just so you notice that the indice on the summation has changed. Here's the solution for the 3rd problem. And that is it for this video. Thank you for watching.